Okay, so here we were. So we had all this nice, nice and interesting property of the guitar model. The model is exactly solvable and everything. So now it's the time to do a sanity check, whether any of this beautiful physics can be realized in real system. So I'm gonna talk about what happens in this three-dimensional material, because it turns out that these three-dimensional materials are actually easier to work with for the reasons that I will explain. And then if I have time, then I will go to this two-dimensional, more recent system that people have been studying. Good. So three-dimensional honeycomb lattice. So hyper-honeycomb lattice and stripy honeycomb lattice. So these systems were discovered in about 3 years ago. So it's not that old. And this is the conventional unit cell of this material. In the primitive unit cell, you have 4 sides. So it's actually a bipartite lattice. So if you look at it, there is no hexagon here. So it's a bit of a misnomer to call it hyper-honeycomb lattice. But the reason why it's called hyper-honeycomb is because each site is connected to 3 other sites. So the local connectivity is the same as the 2D honeycomb lattice. In fact, if you have a 3-dimensional model, if you do the 3-dimensional printing, get the lattice structure, and do the projection of it along certain direction, it looks like a honeycomb lattice actually. But other than that, the smallest loop in this lattice is actually 10-sided loop, not the 6-sided loop. So here, this one is closer to the 2D system in the sense that there are hexagons, but notice that the hexagonal plane here and hexagonal plane here, they are rotated by 90 degrees. And you can alternate between these things, right? So this structure and that structure is different. So when these two materials were discovered, in fact, unfortunate, maybe fortunate thing about this material is that the ground state is not a spin liquid as it is. It orders magnetically at 38 Kelvin. But mysterious thing is that both materials order at the same temperature. So when these two systems were discovered initially, there was a lot of confusion as to like which, whether they are actually the same material or not. So for example, these people thought they got the wrong structure. These people thought that these people got a wrong structure. But it turns out that there are 2 different crystal forms. Both of them are 3-dimensional. And the reason why this system is more ideal is that this material, for example, has much closer to the ideal structure. For example, all the bond length is the same, essentially the same, or the bond angles are extremely similar. You cannot say the same thing for the 2D system. For 2D system, it's actually much more distorted. So we always thought these 2D honeycomb materials are not really an ideal candidate material for the guitar physics. Okay. So the first thing I'd like to show you is that indeed the J-effective half picture is sort of valid. So it's very important to establish this because we want to have a quantum mechanical spin, not some arbitrary mixture. And this ab initio calculation tells you that indeed near the Fermi level is predominantly J-effective half degree of freedom. So we can sort of use this picture. Also, this material has this oxygen octahedra surrounding the iridium atoms, and they are nicely sharing the edges of the oxygen octahedra. Remember that the bond angle has to be close to 90 degrees, and that's actually satisfied. Okay, so the point is this guitar model I talked about can be also exactly solved in these 2 other 3-dimensional lattices. In fact, remember that for the 2D system, you have a Dirac spectrum. The ground state was in the this root product operated to be +1 basically flux sector in the 2D honeycomb lattice. It turns out that if you solve this model, that the model can be solved exactly in the same way, but these C-minor fermions live on a 3-dimensional lattice. In both cases, this minor fermion actually has a nodal line spectrum, not a Dirac spectrum. What is interesting is that in all of the system, if you say compute the heat capacity should be proportional to T square. say, Dirac spectrum in 2D, nodal line spectrum in 3-dimension in both cases. And I also have to mention that for 3-dimensional hyper-honeycomb lattice, the ground state sector is indeed this loop product to be +1 sector. It turns out that for the stripy honeycomb, that's not the case. Actually, it's a little bit more complicated. It's actually in the so-called pi flux sector. But in both cases, the quasi-particle spectrum has a nodal line. In fact, you can think about a series of 3-dimensional lattices going from hyper-honeycomb lattice to, say, this is like, infinite, meaning it's basically totally decoupled honeycomb lattice. You can twist some portion of the honeycomb lattices in such a way that I can generate a series of 3-dimensional lattices, and the guitar model can be solved in all of these lattices. So in fact, this Hamiltonian in any of these lattices has this simple structure that you only have an off-diagonal matrix element. All of these lattices are essentially bipartite lattices. So this means actually these are the matrix elements connecting A and B sub lattices. So if you look at this as a free fermion, Majorana free fermion Hamiltonian, it belongs to so-called BD1 class in this 10-fold way classification scheme for non-interacting TI. So there are certain discrete symmetries you have. In fact, so you can easily see that this structure essentially enforces the nodal line spectrum in 3-dimension. The region is very simple. This is the complex of diagonal matrix elements. So if you require that you have a gapless spectrum, then essentially both the real and imaginary part of the determinant of this matrix element should be 0. You can easily convince yourself that if you require the real part is 0, then you get a sort of surface of a sphere as a 0 energy mode in the momentum space. The imaginary part will give you another surface of the sphere. And when these two spheres intersect, you generate a nodal line, right? That's the reason why you always end up with this nodal line spectrum. And this is again robust to small short range interaction. For example, even if you add Heisenberg interaction, this ground state is going to be stable. Okay, so this is kind of a cartoon picture. This is the momentum space. This is actually the nodal line spectrum that I talked about. And this is an example of topological semi-matter in the following sense. So if you take any trajectory in a momentum space that goes around this nodal line spectrum, along this path, the Hamiltonian is gapped, right? Along this path is basically a gapped 1D Hamiltonian. And you can define a topological invariant using that off-diagonal matrix element of Hamiltonian. So evaluate this object along this one-dimensional, in this one-dimensional, hypothetical one-dimensional system, gapped Hamiltonian. But you have to go around the singularity, namely the nodal line. So if you do that for any line, including the nodal line, then this becomes a topological, integer topological invariant event, and you can show that it's not 0. But if you do this in any loop that doesn't enclose, that doesn't encircle around the nodal line, then you always get 0. So in that sense, this topological, this kind of semi-metal structure has a topological invariant in it. So and you can show that this is protected, sort of this topological property protected by this the BD1 class symmetry. So if you like, this is an example of I would say symmetry enriched topological order, so to speak, because the symmetry enforces this nodal line spectrum, but the underlying ground state is topologically ordered. Okay, and the similar situation arises for the stripy honeycomb. It's a little bit more complicated, but essentially the same idea applies. And if you have this, then you can deform this contour in momentum space. So you can, instead of making a short loop, you can make a long loop by going through this brilliant zone, come back. And each line corresponds to a gapped 1D Hamiltonian. Again, you can show that if you go through inside the ring, then you get a non-trivial topological invariant. If you go outside, then basically it's trivial. So this already immediately tells you that if I go to a boundary surface or the boundary Boolean zone, then the projection of all this bulk momentum position to the boundary surface, basically, if you go to the boundary, the projection of this ring, if you go to the inside of this ring, the projection of the ring, then since any one-dimensional cut in momentum space will correspond to a non-trivial one-dimensional topological phase, you have a non-trivial boundary state. So in fact, you get a localized Majorana zero mode whenever you are inside of this projection of this circle or nodal line. Here, at every momentum position, there's a localized Majorana mode. Outside, it's all gapped out. So you get a sort of gapless, very, very flat band inside this ring, but outside, they are all gapped out. So there's interesting boundary state. Some people call that drumhead surface state. But essentially, that's realized in this kind of system. So it's kind of interesting.
Is it robust against interaction?
The boundaries, I don't think that boundary is robust to interaction. So that's actually an interesting problem. So if I add, so bulk is definitely stable, but the bulk, boundary is not, because boundary has essentially a flat spectrum. So you can imagine that, for example, you can easily induce the ferromagnetic instability at the boundary. So it's kind of interesting problem how it's possible that the surface. So when I add an interaction, it's possible that the surface may go through the phase transition, even the bulk is not. So that's possible. Okay, but now, as I told you, it's not that we have a pure type Hamiltonian. There are all kinds of other terms. So the question is, what happens if I have everything there? So nature has every other term. Unfortunately, these are the only allowed term by symmetry. It's not like arbitrary term in the Hamiltonian is allowed. So we cannot solve this model quantum mechanically. So we decided to look at the classical model first. It's already very complicated, and I don't want to explain what these phases are, and I think that you don't want to know. So I just want to mention that experimentally we know that the ground state is a very complex magnetic order state. It's called incommensurate, non-coplanar, counter-rotating spiral. Okay, but it's some kind of magnetic order, incommensurate magnetic order, and name doesn't matter, right? The physics is invariant under name transformation, right? So it's not important. But point is that so the classical solution of classical model finds this phase. What is interesting is that these phases are actually very close to a Kitaev spin. So this is the Kitaev point. This is the Kitaev point. These are the Kitaev model with the antiferromagnetic interaction. These are the Kitaev model with the ferromagnetic interaction. And we believe that this sign of K is actually ferro-like. So this phase, in principle, is pretty close to the Kitaev spin. So we may not be far off. It's just that since I cannot solve a quantum model rigorously, we don't know, for example, in the classical model, it's just a single point. We know that there should be a finite region here around here. We don't know how small that is. But as long as there's a finite extent, if it's not too small, the very fact that we have this interesting magnetic order means that we may be very close to the Kitaev point. And in fact, one can show that without Kitaev interaction, you cannot get this magnetic order state. So one thing we know is that this Kitaev term has to be quite big. Otherwise, you wouldn't get this strange magnetic order here. Okay, so that's the good news. Another news is that, so I cannot do this calculation, but my collaborator did. So they did some sort of ab initio derived spin model. So they can estimate the values of J, K, and gamma. And indeed, they found that if for reasonable parameter set, you are somewhere around here in the phase diagram. So notice that this is just solving this model. And it's not so clear where the real materials are here, right? We're just solving a model. So, so I don't know what the values of JK gamma is. It's entirely possible the real materials are here, 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 not here. Yeah, so you have to check. And according to this microscopic calculation, indeed, we are somewhere here. So microscopics agree with the prediction from the classical model. So that's kind of nice, because this kind of non-trivial check. So you may be very close to here, but they're not quite there. Okay. So now you may say, well, you get a magnetically ordered state, so the answer is not interesting, right? Because we didn't get a spin liquid. But notice that this is the benchmark test for the Kitaev interaction. Because without sizable Kitaev interaction, we cannot even get this magnetic order. So it's a proof that the Kitaev interaction in this kind of material is quite large. Secondly, so Kitaev interaction is actually dominating in this three-dimensional material. Also, very recently, when you apply a 2.5 gigapascal on a beta material, actually there's also a high pressure experiment on the gamma materials too. It turns out that the magnetic order disappears. And it looks as if the resulting state may be a gapless spin liquid, in the sense that according to NMR measurement, the night shift and also the spin lattice relaxation rate shows some power law in temperature dependence, and that suggests that maybe this paramagnetic that you obtain after applying a pressure is a quantum spin liquid. I think it's still not published, but even after 2 years. But that doesn't mean the data is wrong, right? Okay. So again, you can do a microscopic calculation on the pressure and try to see how JK gamma changes. So initially, a lot of people speculated that under pressure, perhaps what's going on is that originally you are here. Under pressure, maybe you're approaching the Kitaev limit. Then naturally you get some sort of Kitaev spin liquid, right? With some kind of nodal line spectrum. There will be a gapless spin liquid. So that's sort of what we were trying to obtain by doing this microscopic calculation. So you can do this ab initio type calculation and try to see how JK gamma changes. So what's interesting is that it turns out you are actually not approaching the Kitaev limit. You're actually going away from the Kitaev limit. But you are approaching a different limit. So it turns out if you're approaching the center of the phase diagram that I didn't quite explain, it turns out that when you move to the center of the phase diagram, you're actually entering the gamma interaction dominating regime. So this becomes the biggest energy scale. K becomes smaller, but gamma becomes the biggest energy scale. So why this is interesting? So even though there's no exact solution of the gamma model, we know that if you solve a classical model, then there is a macroscopic degeneracy. Again, you end up with a macroscopically large number of equally unhappy classical ground state. So in a way, there's a source of the frustration, and maybe there is a reason to believe that this gamma model, if somebody can solve it, maybe one of you can solve it. If you can solve it, then ground state may turn out to be a quantum spin liquid. So the point is that in that limit, there is a hope that when you are entering a gamma dominant regime, you are actually getting into a new kind of spin liquid. It may not be a Kitaev spin liquid, but something else. Yeah. So that's sort of the idea. So it's an unsolved problem. So you are encouraged to solve it, right? Okay. I couldn't do it. So good. Right. I think I'm going to skip this. Okay. So I'm going to move to a two-dimensional system. So this came as a surprise. So this is, in this material, the ruthenium ions are making a honeycomb lattice, and the chloride is making a sort of making an octahedra around the ruthenium ion, and they make a edge sharing structure, so that you can realize the Kitaev physics. Okay. So this material also orders magnetically at 7 Kelvin. So you can see that from the heat capacity data. And neutron scattering, clearly see the magnetic ordering. So this is one of those zigzag type magnetic ordering pattern. But what is interesting, though, is that in this system, you can actually do a neutron scattering to see a spin excitation spectrum. And they see some kind of continuum of scattering. So this is the neutron intensity as a function of energy. And in the low temperature, remember that ordering temperature 7 Kelvin. So this is below magnetic ordering temperature. This is above magnetic ordering temperature. And this little peak represents the spin wave excitation of the zigzag magnetic order. On top of that, there's some kind of scattering continuum that extends from low energy to intermediate energy scale. So it's somewhat spread out. And this scattering continuum is a 2-dimensional. It has a 2-dimensional dispersion in it. And this scattering continuum doesn't die above magnetic ordering temperature. So this scattering continuum exists both below and above. And even in the ordered phase, it exists on top of the spin wave excitation. And this is pretty unusual for the quantum magnet. You know, usually Goldstone mode, the spin wave is well separated from any continuum of scattering. Like, for example, you may have like 2-megaton scattering continuum, multi-megaton scattering continuum. But in a well-ordered magnet, they're all very far away. So clearly, this is not usual 2-megaton continuum. Also, if it is a 2-megaton continuum, they are not going to survive above ordering temperature. So the underlying idea is that this continuum of excitation seen below and above temperature may be a signature of nearby quantum spin liquid. And you can sort of, and that's a remnant of, say, proximate, so to speak, spin liquid phase. For example, the idea is that if you apply some perturbation to the system, either applying a magnetic field or pressure, you may get into a nearby quantum spin liquid. And then you may be seeing the two spin-on continuum from those proximate phases. That's basically the idea. And another important discovery in the experiment is that when you look at the neutron scattering intensity, this is a 2-dimensional Brillouin zone cut. They see this so-called Staub-David intensity distribution at low energy. So I didn't draw the Brillouin zone, but first Brillouin zone, if there's a star shape, those guys are actually pointing so-called M point in the Brillouin zone. The familiar K point is in somewhere in between. And then this kind of intensity is not what you expect from the pure Kitaev model. So clearly, the pure Kitaev spin liquid is not going to explain this kind of intensity distribution in the scattering continuum. So something else is going on. In fact, very recently, by applying a magnetic field, you can actually suppress the magnetic order. So, for example, look at the 2 Kelvin data. This is the elastic neutron scattering data. The magnetic intensity goes to 0 above like 8 Tesla. So above 8 Tesla, it becomes paramagnetic. So this zigzag magnetic order actually dies around the 8 Tesla. And this is a quantum paramagnet. So some people speculate that this quantum paramagnetic state could be a spin liquid state. So the question is, if it is a spin liquid state, what kind of spin liquid phase it is, right? Is it a Kitaev spin liquid or something else? Good. Again, it turns out that even though ruthenium ions are 4D element, not the 5D element, so in principle, spin-orbit coupling is smaller. So you may not expect that the splitting between pseudo-spin half and 3/2 degree of freedom is not well separated. Indeed, if you just include the spin-orbit coupling, then they are pretty well mixed. But interestingly, if you add the interaction, say small Hubbard U, then that interaction, the interplay between spin-orbit and the Hubbard U interaction somehow makes this separation sort of better. So the situation improves considerably when you add the interaction. So in the end, with the reasonable strength of spin-orbit and Hubbard interaction, you can see that this material, the local moment, can be described by the J-effective half picture. So this sort of microscopic justification to think about ruthenium ions as a local pseudo-spin half local moment. So again, according to these people, they estimated sort of those couplings in the Hamiltonian. So it turns out that the biggest coupling is nearest neighbor type interaction, and then nearest neighbor gamma interaction is also quite big. In fact, according to this calculation, if you believe it, the strengths of the K and gamma are comparable to each other.
Is the structure known experimentally?
Yeah, it's actually structure is known very accurately. So it's based on experimentally determined structure. And then the next biggest term is the third neighbor Heisenberg interaction. It's kind of interesting, right? The nearest neighbor Heisenberg interaction is quite small. So these two are the dominant interaction. This is the next leading order interaction. But it's already much smaller than these two other interactions. So, so we decided that we are going to look at this model as a minimal model. So think about this model as a minimal model. So there's a K-type interaction. Then in addition to that, there's this gamma interaction. This is what we call K-gamma model. So So if, for example, look at the G bond, the green bond, this was the K-type interaction. Now along that bond, as I told you in the previous lecture, the gamma interaction is actually has this off-diagonal form, xy plus yx type. So this model can be solved exactly, K-type model, but the gamma model cannot be solved exactly as far as I know. We couldn't solve it. It's actually not so trivial. So, so we decided to look at this model. So by introducing this cosine phi and sine phi, by changing phi, I can change the Hamiltonian. If phi is 0, then I'm at the ferromagnetic K-type point. If phi is pi, then I have anti-ferromagnetic K-type. If phi is pi by 2, then I have a pure gamma model without any K-type interaction. Okay, and for the reasons that I will explain, we decided to introduce some anisotropy in the K-type interaction. So the xy are the same, but the G bond is slightly different. So so A is an anisotropy parameter. Okay, so the first thing we did was to look at the finite size cluster calculation. So you do exact diagonalization on the 24-side cluster. Here we introduced anisotropy parameter like 0.1, so it is 10% anisotropy. Then the claim is that if you look at the ground state energy as a function of phi, remember that this is the K-type ferro K-type limit, anti-ferro K-type limit. This is the pure gamma model. And the point is that we don't see any evidence of phase transition between phi equals 0 and all the way to phi equals to around, say, 0.6. But then you enter then you enter a new phase. So this represents a phase transition where there's a magnetic order. For example, if you look at the static structure factor at different position in the momentum space, and this is what you get. And around here, when the K-type interaction has an anti-ferromagnetic sign, here you get some kind of long-range order. And when phi equals 0.75, you can show that there's some kind of hidden SU2 symmetry. You can do what people call 6-level lattice transformation. You can make a transformation to that Hamiltonian at that particular point. It maps to a ferromagnetic Heisenberg model. So there's a hidden SU2 symmetry. So the ground state has to be a product state. And there we know the exact solution. So obviously the ground state of ferromagnet is just a ferromagnet. But then you do a 6-level lattice transformation back to the original basis, and you find that the magnetic order is some kind of 120-degree order. So in fact, in all of the phases here between, there's a magnetic order here. So this magnetic order we understand very well. But looks like between here and here, there is basically no magnetic order. So imagine that I believe this thing, right? So this is 24-side cluster. So some people may believe it, some people may not believe this result. There are strong finite size effect. So, but if there is no transition here, what that means is that, say, if phi equals 0.5 here, phi equals 0 is the K-type spin liquid, they are adiabatically connected. They are continuously connected. So this phase here, that phase here, they could be cousins to each other. And if that's the case, that's very interesting, right? Because even though we don't have exact solution here, if the ground state here is continuously connected to this one, then we can say everywhere here will be a quantum spin liquid state. And that will be some sort of G2 spin liquid, right? That will be the hypothesis. Yeah. So in fact, we change the anisotropy parameter. Then we find that between 0.06 and 0.5, essentially this is what we find. There's really no change in between this point and that point. When you don't have anisotropy, when A equals 0, that's the original model, then we find that there are a lot of finite size effects. So we couldn't conclude anything, essentially, because essentially, depending on the system size, we look at 18, 24, 32. You see all kinds of stuff when A equals 0. But between these two limits, basically everything is quiet. So when I first saw this graph, I told my student that this is too good to be true. Yeah, yeah. This has a dramatic consequence. Okay. But there are some other computation that's encouraging. For example, using this approach, you can compute the static structure factor by changing phi. So by basically increasing the strength of the gamma. Then you find that when the strength of the gamma becomes bigger, essentially the static structure factor has this star Davy shape intensity, right? Basically, the intensity is not just at the gamma point, but it extends to the end point of the Brillouin zone. And remember that for the Kitaev model, you don't have this structure. Actually, for Kitaev model, it's pretty isotropic. That's one of the characteristic properties of the Kitaev spin liquid. There's really no momentum dependence. But here, there is a characteristic momentum dependence that resembles the experimental data. So maybe there's some truth in it. Introducing gamma is doing this job. So another interesting test we did is as follows. So the ground state of this model, as I say, is in the zero flux sector. But at finite temperature, you can excite some excitation. One of the excitation you can create is some flux excitation, meaning that if you measure the loop product operator at finite temperature, some flux may have a pi flux in it. So this is W can have a -1 for some loops, right? So these are the gapped excitations, but at finite temperature you can excite them. In fact, you can solve this Kitaev model at finite temperature. This is the data from these three gentlemen. So this is with the isotropic limit. This is with the slight anisotropy. And if you look at the heat capacity of the Kitaev model at finite temperature, this is the exact solution. You can see two peak structure in the heat capacity. It's more pronounced when you introduce anisotropy here. And the interpretation is as follows. So this first peak corresponds to exciting the flux degree of freedom. In fact, that energy scale is the energy scale of the flux excitation. The second peak is just the emergence of short-range spin correlation. Basically, above that, the system is essentially classical. So when I come down in temperature, when you first encounter this peak, you develop the quantum short spin correlation. Then basically below this line, you are entering a ground state. So yeah. So if you're within this temperature window, then you still have a Majorana fermion, but your Majorana fermions are moving in the background of thermally excited fluxes. So below this temperature, basically there's no flux excitation. So ground state essentially discarded phase. Between these two temperature scale, is that you have a thermally excited fluxes. That's essentially the characteristic features of the heat capacity. Okay, so what happens is that we took this model, then you compute heat capacity as a function of temperature. So this is a BG plot, so I'm gonna separate this thing. So you look at the Kitaev limit, and indeed this calculation reproduces the exact calculation done by Motome. you have a two-peak structure in the heat capacity. Remember that this one corresponds to exciting flux degree of freedom, this development of short-range spin correlation. And when you go to a pure gamma limit, interestingly, you still have a two-peak structure. In between, you still have a two-peak structure. In fact, everywhere in between, you get a two-peak structure. Okay. So the question is, can you really interpret the first one as an exciting something like flux degree of freedom? I mean, I think that the second peak, the origin of second peak is universal. That's really the development of short-range spin correlation. But perhaps the first peak can be interpreted as the exciting flux degree of freedom.
So what are the two energy scales here? Like one should K.
That's right. So this will be, this energy scale will be, let me see, exciting flux degree of freedom. That should be related to K. Yeah, that's right. That should be related to K.
The higher one is because of gamma?
Actually, both of them are some combination of K and gamma. So that's why this energy scale actually moves around. It's not exactly the same, right? This energy scale actually moves around. Right. Also, if you add small J3, then you can see that the zigzag magnetic order is significantly enhanced. So this supports the scenario that if the K gamma model may support the quantum spin liquid, but if you add this third neighbor Heisenberg term, and that may be the reason why we see a zigzag magnetic order. So we were not satisfied with this, so we decided to look at this K gamma model on a beta lattice. So this is one version of the tensor product wave function approach, but since it was not easy to solve the 2D problem, we decided to look at this beta lattice. So beta lattice means every site is connected to 3 other sites. So local connectivity is exactly the same as the 2D honeycomb lattice, but basically there's no loop, right? That's basically the definition of beta lattice. So but is it infinite? By definition, this is the infinite lattice. So we, by introducing one isotropy parameter, we can actually look at the entire phase diagram. Again, if you look at the magnetization, the magnetization order parameter, broken symmetry, exists only at the positive K, the antiferromagnetic K limit. The integral entropy is finite, is high, along everywhere in this part of the phase diagram, and I told you that at phi equals 0.75, there's a hidden SU2 symmetry, so the ground state is a product state, and indeed in this calculation, it nicely tells you the integral entropy is exactly 0, as it should be, because it's actually a product state. So in the ordered phase, integral entropy is pretty small, but in the paramagnetic state where there is no magnetic order, you do see a high entanglement entropy, and ground state energy really doesn't show any kink or anything in that beta lattice. So for the beta lattice, this is essentially exact solution, right? Numerically exact. So we know that along the beta lattice, this one really corresponds. All these phases are really connected to the Kitaev limit. You can solve Kitaev model on this lattice. It's kind of trivial. It's like a zero-dimensional Kitaev model, if you like. So, but these phases are all connected to each other. Okay. So also, there's a way to compute the dynamical structure factor. So the one I showed you was a static structure factor, but there is a way to compute the dynamical structure factor. And indeed, in the low energy limit, you do see this star of Davis structure. So there's sort of evidences suggesting that this kind of approach may actually explain the experimental data. Okay, so I don't think that I'll have time to explain, but we also have IDMRG results that we are still analyzing. It's actually very complicated. So, the results are not quite ready to show you. But but the claim is that the results are actually pretty similar to this one. So we think that so again, the integral moment entropy is pretty high compared to the ordered phase. And we think that there is no phase transition really between phi equals 0 and phi equals 0.5. Okay, so yeah, okay. So now I'm going to switch the gear and talk about something different. So I'm not going to talk about spin liquid, but other kinds of system. So this is the series of material called particle iridae. So here, R represents the rarest ion, and iridium ions are same iridium plus ion. So it turns out iridiums are sitting on a particle lattice. Particle lattice is a corner-sharing tetrahedron. The rarest ions are also sitting on a particle lattice, but in a different particle lattice. So this lattice consists of two interpenetrating particle lattices. By changing this rarest ion, you can change the metal insulator transition. At high temperature, the material looks like a metallic. In the low temperature, you get an insulator. It turns out that these insulators are magnetically ordered, but this metal insulator transition temperature can be changed dramatically. For example, for praseodymium ions here, the system remains metallic all the way down to 0 temperature. And it turns out that this magnetic order is a very special magnetic order. It's called all-in, all-out magnetic order. So in one tetrahedron, all the spins are pointing to the center of the tetrahedron. In the next tetrahedron, they're all pointing out. So interesting thing about this magnetic order is that it doesn't break the point group symmetry of the system. It only breaks tiny boson. It doesn't break translation symmetry. And that's going to be important. So again, using this J-effective Hart picture, you can construct some sort of tight bonding model. Then you can add an interaction, and then study the interacting model. And this is sort of Hartree-Fock phase diagram here. So this is the interaction measured in terms of hopping strengths. And there are two kinds of hopping. The T1 is the spin preserving hopping. T2 is the spin flip hopping. And this spin flip hopping is there because the underlying system has a strong spin-orbit coupling. Without spin-orbit coupling, you only have a spin preserving hopping. And this Hamiltonian is written in this J-effective Hart basis. So notice that even without interaction, the phase diagram is kind of interesting. So depending on the relative ratio of these two strengths of the hopping, you can have a topological insulator, for example, with a positive T2. And with a negative T2, you get what we call quadratic band touching semi-metal. This little figure represents the quadratic band touching. Then you can also have a metallic phase with a small electron hole pocket. When you increase Hubbard-U interaction, then you eventually enter the all-in all-out magnetic order. Here, it turns out you get a slightly different kind of magnetic order, but the real material is in this regime of the phase diagram. And what is interesting is that when you go from here to here, you almost have to go through the intermediate phase called Weil semi-metal. And this is the semi-metal with the three-dimensional Dirac points in the bulk. And so I like to emphasize that the magnetic order already exists here in the Weil semi-metal. It's just that it doesn't open up a gap immediately. So for example, if you look at the single particle spectrum, so this is the quadratic band touching semi-metal spectrum. You see a quadratic band touching at the gamma point. And you know that when there's a tiny boson symmetry and inversion symmetry together, that every band has to be doubly degenerate. So in fact, this one, every band is doubly degenerate, and they are touching at the Jones center quadratically. But when you enter magnetically ordered state, then the band will split. Band degeneracy is not protected anymore. So when this quadratic band touching split, and you can easily generate this crossing of two non-degenerate level, and they always come in pairs. And so there's another one. I'm showing only one. And that exists between gamma and the L point. So L point is along the one-on-one direction in the Brillouin zone. And then when you increase Hubbard-U, this Weil point, the crossing of the non-degenerate level, moves to the high symmetric position, in this case L point. they annihilate, they open up a full gap, then you enter a trivial insulating state. So the point is that if you start from a codec band touching, you always have to go through this Weyl crossing in the system. So people have been hunting for this Weyl semi-metal for a very long time. In this kind of material, actually the Weyl semi-metal was initially proposed for this material, but it was never really found yet. But it was found in semiconductor system. So now we know a lot of examples. But all of these examples in semiconductors, they are all inversion symmetry breaking example. There's no example of tiny muscle symmetry breaking Weyl semi-metal in semiconductor system. You see, the reason why here you get a tiny muscle symmetry breaking Weyl semi-metal is that you actually enter the magnetically ordered state. Yeah? In semiconductor system, you don't have a magnetic order. So the easiest way to generate Weyl formation is actually break the inversion symmetry, not the tiny muscle symmetry. But here we are doing something different. We are not breaking inversion symmetry. This magnetic order doesn't break any lattice symmetry, remember? It only breaks tiny muscle. So in a way, this is slightly different from all other Weyl semi-metal that's already discovered. But nonetheless, this is what is supposed to happen. So this is not observed yet, but the codec band touching has been observed. For example, remember that for pristine imidite, this material becomes remains paramagnetic down to very low temperature, so that you can actually do a RPS measurement. I'm not going to go into details, but they see evidence for codec band touching in this material. So some efforts are underway that if you mix presidium with some other elements like a neodymium, you can develop the magnetic order with a very small TC. Then hope is that you can see the transition from codec band touching to the Weyl semi-metal. So that will be one of the experimental programs that people have been pursuing. Another interesting thing we did was that you look at the codec band touching system. They imagine that I put a long-range Coulomb interaction. And the reason why this is interesting is that when you have a codec band touching, the density of state is very small, right? Especially compared to a Fermi surface system. So your Coulomb interaction is actually not very, very screened. So the effect of Coulomb interaction becomes actually quite important. In fact, one can show that if you do a renormalization group analysis with this long-range Coulomb interaction for the codec band touching, this leads to some kind of non-trivial interacting fixed point. And that's described by non-Fermi liquid scaling. And I like to emphasize 2 points. The first point is that the original model is a lattice model. So it has a cubic anisotropy in it. The real crystal has a cubic anisotropy. So we started with a model with the cubic anisotropy. In the interacting fixed point, this cubic anisotropy becomes irrelevant. That's kind of interesting. So it becomes actually an isotropic model. So all the properties are isotropic. There's no cubic anisotropy at the fixed point. Also, this analysis is essentially exact as long as RG is valid. And in fact, this is probably the first example of control solution of non-Fermi liquid in any gapless system with the interaction. All other models have a lot of issues. So using this, we can predict various exponents for physical quantities, like, for example, non-linear susceptibility is supposed to be divergent with some characteristic power law, and et cetera, et cetera. Okay, so I think that this is another thing that experimentalists may be able to test in the future. So actually there is a very, very interesting property associated with the Weyl semi-metal and also chiral anomaly. So I'm going to explain very briefly here. 5 minutes, okay. So actually, I have to finish in 5 minutes. I have to catch a flight. So you always create a pair of Weyl points in the Boolean zone. They are opposite chirality. And once you create this thing in the bulk of Boolean zone, it's pretty stable. It's very stable, and the region is very simple. So in 3 dimensions, for each momentum direction, you can assign 1 Pauli matrices. But after you use up all the Pauli matrices, there's no other anti-commuting 2x2 matrices. So you cannot generate a mass term. So its phase is very stable. The only way that you can destroy them is to make them to pair annihilate. Now, these people discover that this file CML has a very interesting boundary state. So if you do the projection of this file point, the surface Brillouin zone, and they think about a two-dimensional cut that's connecting these two points, then you can show that this two-dimensional system acts like an integer quantum Hall state with the chart number 1. So what that means is that at the boundary, there must be a one chiral edge mode. So I'm going to skip this. There should be one chiral edge mode. You can do the same for next plane. But when you get out of it, this 2D system becomes trivial, basically chart number 0. So what that means is that this boundary state should end here. It cannot continue. So this gapless boundary mode can connect only these 2 points. It becomes a Fermi arc. So it's looks like that. And the point is that the other part of the Fermi arc is at the other boundary. So in a way, you're separating this closed loop into 2 pieces physically. They are actually far away from each other. Okay, so if you have only one pair of wild points, you can easily convince yourself that you should get a pretty big Hall conductivity, because as I said, every plane between these 2 points acts like a quantum Hall state. Everyone carries E squared by H Hall conductivity. So if you add them up, it's going to be like I have to multiply them by the distance between 2 points. So I should expect to see a humongous Hall conductivity. And this doesn't happen in this material because there's actually other wild points related by cubic symmetry. Actually, there are 8 wild points. In real material, actually, there are 24 wild points. But they're all related by symmetry. So they sum them up to be 0, unfortunately. So cubic symmetry makes sure that they all sum them up and net result is 0. But this can be fixed, for example, by making a film of the system so that you actually break cubic symmetry. So if you grow this system, 3-dimensional material, but you can grow on a substrate, you can actually grow them layer by layer. Then your cubic symmetry can be lost. Then, in principle, you can create a large Hall conductivity. And I'm not just saying it. This experiment is done. I think that the paper is submitted to either Nature or Science. It was done in Japan. And indeed, you see a large Hall conductivity, anomalous Hall conductivity, because of the surface state, I think. I think that this thing is actually quite real. So I think I'd like to end my talk here. Thank you very much.